Hillebrand Prize. This is our major award we give every year for excellence in the chemical sciences over the course of a person's career. This year's recipient is Dr. Let me make sure I pronounce this. Hopefully I pronounce this correctly. Dr. Zakya Kafafi, who has had a long career at the Navy Research Lab in study of organic, optical, and electronic materials, and has become a world-renowned expert on the subject.
Good job.
Receiving a chemistry prize has a special meaning to me. As a chemist, I joined the ACS, the American Chemical Society, probably 40 years ago, and when I arrived in Washington, D.C., more than 30 years ago, I joined the Chemical Society of Washington. This is longer than any professional society to whom I belong, either as a member or as a fellow. Let me begin by telling you a bit about myself and the people that influenced me in my career and in my journey here. I was born in Cairo, Egypt, in a hospital overlooking the Nile River. So I guess you may call me the daughter of the Nile. So I guess you see this satellite picture, and it gives you, the location of Egypt within, that is clearly seen from about 40,000 kilometers or so. I would like to dedicate this award to my parents, Hussein Kafafi and Madiha Tolba. They both influenced me in very different ways, but they both inspired me in pursuing my dreams. Actually, yesterday was my dad's birthday, and I know for sure that he would have been thrilled to be here with us tonight. I am the oldest of three girls, Zakya, Jihan, and Laila. My mother insisted that we receive our education from a liberal, non-pedagogical private French school called Lycée Français du Caire. My father was very influential on us in pursuing a higher education. The last recording of his voice that I still have but never played it again was his advice to me to pursue my graduate studies. In his own words, he said, at least a master's degree, if not a PhD. I left Egypt to Houston, Texas when I was 18 years old after graduating from high school. I majored in chemistry and I minored in math. My love and passion for chemistry actually started in high school when I was introduced to the subject matter for the first time by Monsieur Georges, our teacher in chemistry. He was a great teacher. He used to call me the chemist, and I'm not sure really why. 6 years later, I received my bachelor, master, and PhD degrees in chemistry and was blessed with 2 beautiful children. And this is actually the graduation ceremony from my PhD from Rice University. When my dad passed away a year just before I graduated from college, I continued to carry his torch and was able to convince my 2 sisters, Jihan and Laila, these are nicknames, Zizi, Gigi, Lily, to come to America and pursue graduate studies. A few years later, Jihan got her PhD in applied economics from the Wharton School at UPenn, for Wharton School of Business, and Lila got her PhD from Duke University in sociology and demography. When I joined the chemistry department at Rice University for my graduate studies, I went to many seminars offered by the faculty members. Each one was trying to sell his or her research area. It was primarily his research area. There was only one woman faculty at the time. And I was intrigued by one of the research areas that John Margrave was pursuing. And for this reason, I chose him as my thesis advisor. It was a research area in the area of infrared matrix isolation spectroscopy, which is really doing spectroscopy of high temperature at very low temperatures, cryogenic temperature. Here you see me. This is actually taken from my PhD thesis in front of the apparatus next to this liquid helium door. I used to drag this helium door from the 3rd floor in chemistry down the elevators and cross the street to the physics department, the 1st floor, to fill it each time it was empty. I actually did that even when I was pregnant with my son until I gave birth to him just a few days before. On the day when I was running the experiment, you see here a liquid helium transfer line, I always try to make sure and remind myself that I need to wear slacks that day. And the reason is I had to get up on a table very high and slowly holding this liquid helium transfer line and slowly lowering it to the liquid helium door on one end and to the matrix isolation apparatus on the other end. This is the way in the old days when we cooled the substrate where we prepared our matrix. It had to be very, very cold. And we were able to cool the matrix surface to 4 degrees Kelvin. This is like 4 degrees above absolute zero. Do you know what 4 Kelvin is? Somebody knows? In Fahrenheit or centigrade? In Fahrenheit is minus 453 Fahrenheit, and in Celsius is about minus 269. Matrix isolation was developed by Georges Pimentel at Berkeley in the 50s. Georges was interested in studying free radicals, which are very unstable species. He then came up with the idea to trap these unstable species in a solid cooled at very, very low temperature. So he wanted to do that in order to prevent molecular diffusion and enough high concentration for direct characterization, which was primarily spectroscopic studies. His first experiment actually was quite dangerous. He used liquid hydrogen to cool the substrate, which is very, very flammable material. And he used inert gas matrices like argon, xenon, krypton, neon, not neon, but argon and krypton and xenon primarily. He selected these materials due to their chemical inertness and to their transparency. They are transparent from the very far infrared all the way to the vacuum UV, ultraviolet. In his case, he selected infrared spectroscopy. Infrared spectroscopy measures the different vibrational modes of the molecules. A molecule vibrates, it can be stretching, it can be bending, it can do different modes, and from this infrared spectra you can determine the structure of the molecule and many other properties. You can also use isotopes of some of the elements to identify the particular molecule and its structure. So using this powerful technique, he was able to trap methyl radical, as I said, is very unstable, and characterizes through infrared matrix isolation. One of Pimentel's students, Jerry Richmond, just received the Priestley Medal last week at the American Chemical Society that was held in New Orleans. As a Priestley medalist, Jerry Richmond made her mark with insight about water-oil interfaces and water-air interfaces. However, her contributions go beyond chemistry and science and beyond the lab. She helped found COACH, which stands for Committee on the Advancement of Women Chemists, an organization dedicated to giving women skills for successful careers. She also served on the National Science Board of the National Science Foundation as the AAAS president and as a science envoy in Southeast Asia for the US State Department. All of this at the same time as she was teaching and doing research. There are actually two nice articles on her, including her Priestley Medal speech in the March 19th issue of Chemical and Engineering News, what we call ChemSCN News. One of the scientists that indirectly and directly had a great influence on my career was the late Marilyn J. Cox. Marilyn was a dear friend and colleague and a mentor. I was first introduced to Marilyn when I was a graduate student at Rice University, pursuing research in matrix isolation. I came across many excellent papers co-authored by J. Cox and Milligan and J. Cox. This was followed by meeting her in person in many conferences like the Gordon Research Conferences on matrix isolation, spectroscopy. Later on, when I moved to Washington, D.C. to work at the Naval Research Lab, Marilyn and I discovered we shared the same birthday. And from there on, we started celebrating our birthdays together, mutual birthdays together, in great restaurants discovered by Marilyn. She had an exquisite taste for good food, and for a few occasions, I was lucky enough to sample her own eclectic cuisine and gourmet meals. When Marilyn was close to turning 70, I initiated an effort to honor her accomplishments in matrix isolation. I called a dear friend of mine and a colleague, Mustafa El-Sayed, who then was the editor-in-chief of the Journal of Physical Chemistry. And I proposed to put together a special issue of JPhysChem in celebration of her 70th birthday. Mustafa accepted the proposal that Lester Andrews, Bruce Alt, and I submitted. A year and 1 day later, after her birthday, the Marilyn J. Cox Festschrift, with 50 contributions from colleagues and collaborators, was published in honor of her work and accomplishment. Here I show you a picture of what I call the odd couples. They are not really couples, as you may think. They were colleagues, Marilyn J. Cox and Dolphus Milligan. She was about 32 years old before joining the National Bureau of Standards, which is now NIST. And Dick Milligan was about 42 years old before his tragic, 2 years just before his tragic death. They were partners in research for 15 productive years. Marilyn was very active in promoting women scientists and worked hard to achieve their equality with fellow men scientists. She was among the 6 recipients of the 1973 Federal Women's Award when she was invited to the Oval Office of the White House to meet President Nixon at the time, who said to her, "You ladies don't have anything to complain about. The government is treating you well." She remarked, "Yes, but we are the lucky ones." and began to quote the statistics recently published in NBS about the average grade level of women, which were 3 grade level below those of men. Marilyn's passion and devotion to promote women scientists led her to serve on various committees and work hard to achieve their equality with fellow men scientists. As a result of this effort and other activities, in 1991, she received the WISE Lifetime Achievement Award of the Interagency Committee for Women in Science and Engineering. She also was the recipient of the Hillebrand Prize in 1990. A few years ago, I had the honor and privilege to celebrate her life and accomplishment with her colleagues and friends at NIST. Now coming back to my career in chemistry. After I got my PhD, I moved back to Cairo for a few months before moving with my family to London, England. Due to various circumstances and reasons, I did not work for a few years before assuming a faculty position in one of the universities in Cairo, where I was primarily teaching and couldn't do much research due to the lack of equipment and facilities there. A couple of years later, I came back to the US on a short sabbatical and chose to go to my university, Rice University. This was 9 years later after I received my PhD degree and did not do any real research. I was anxious and scared that I missed the boat in terms of research. I recall very clearly standing in front of the same equipment where I did my PhD research and freezing. I was totally frozen. It was a very embarrassing moment for me. From there, I started my race. I was privileged to work with 2 talented chemists, the late Robert Hauge, who originally trained me during my graduate studies, and Leif Frieden, whose daughter Lisa, where are you, Lisa? Is in the back here. She is a chemist whom I met when I was on my sabbatical at Northwestern University, and Lisa was defending her PhD thesis. So she is the one who reconnected me to my colleague Leif and his wife also, who's a colleague, dear colleague of mine, Jan. And they all came to her PhD defense and we reconnected, and actually we had lunch, we had dinner with her parents just a few weeks ago when we attended the American Association, the annual meeting of the American Association for the Advancement of Science. So together, Bob, Leif, and I designed and built this very sophisticated matrix isolation apparatus, which is interfaced to a Fourier transform infrared spectrometer. We won the IR 100 award for a special feature that we designed in this apparatus, and I'm enlarging it here. This is the matrix surfaces. We developed a multi-surface apparatus that can translate vertically and rotate in vacuum while maintaining very cold temperature, and that's very difficult to do. This apparatus that had 5 levels, this apparatus was used 24 hours a day, 7 days a week by many graduate students and postdoctoral fellows. Now I'll give you a couple of examples on the type of work I've done using the technique of matrix isolation spectroscopy, and which was the focus of my research or my early research. And the focus at the time was what we call inert bond activation, and I'll explain that to the non-chemists in the audience. So one of the simplest reactions we studied was silicon with molecular hydrogen. The way we came across this chemical reaction was really serendipity. We're doing some studies on silicon atoms with other molecules like water, and we kept seeing these peaks in vacuum that we could not identify them and we could not relate them to the other experiments. So since they were in the position of a silicon hydrogen stretching region, we thought it might be a product between silicon atoms and some hydrocarbon or hydrogen. So we launched this study to look at the reaction of silicon atom with hydrogen. And we confirmed that these peaks are indeed the product of silicon activating an HH bond. Activating an HH bond meaning breaking this H bond and inserting in it. So we form what they call a silane or SiH2. And initially it was formed in its electronic excited states, and then it decays to its ground state. So in the presence of excess hydrogen, we also saw other products like silane and disilane, which are very important products in the semiconductor industry. In order to confirm the identity of these products, what we do because we are doing the vibrational modes, we can replace hydrogen with its isotope, molecular deuterium, and you can see, and then we can look at the shift in the vibrational, in the stretching vibration mode, and it can be calculated, and we did confirm that it was silicon silane or silicon, inserted in the hydrogen bond. One of the fun experiments that we did, we want to not only react silicon with D2 or H2, which is molecular hydrogen deuterium, but we wanted to also react it with HD. And this experiment, we had to then react molecular hydrogen with molecular deuterium to make HD. This is a very exothermic reaction. So it's really a little explosion. So we had to be very careful to introduce a small amount of molecular hydrogen and molecular deuterium to make HD. And every time we turned the valves to introduce these two species, we heard a noise, which was really a small explosion. But anyway, this helped us, succeeding in determining the identity of these species. And we concluded, we were able then to solve this puzzle of these unknown peaks and concluded that the reaction of silicon atoms came actually from the cracking of diffusion pump oil, which is the hydrocarbon, the pump oil that's used to create the vacuum, and the hydrocarbon crack on the hot surface of the pump oil and create these species. So whenever you have diffusion pump, you'll have a small amount of molecular hydrogens in vacuum. Another reaction that I would like to share with you is a little bit more complicated, but it's related to the reaction of iron atom with ethylene. And this is important in the chemical industry, where metal are used as a catalyst for producing many chemical products. So what we found that was intriguing, and this is, I'll show you here different spectrum in the CH stretching region and the carbon-carbon stretching region. What we found that the iron atom reacts differently with ethylene than di-iron atom, the two iron together. So here you formed what we find that it forms a hydrogen bonded complex, which was a surprise. The chemists in the audience here will expect that the iron will actually interact with the pi system of the carbon-carbon double bond of ethylene, but we formed, and this is, we saw the perturbation in the CH stretch of ethylene here. So this is different spectrum to subtract all the ethylene products. In this case, we look at the carbon-carbon stretch and we see perturbation on it, signaling that we have di-iron forming a pi complex with ethylene. When we irradiated the matrix with ultraviolet light, we noticed that this product disappeared, and we noticed a peak in the iron hydrogen stretching region, signaling again the activation in this case of the CH bond. So iron atom in this case inserted into the CH bond to form these vinyl iron hydride. This reaction was photoreversible, so if you shine light on the matrix with visible light, you get back the iron hydrogen bonded complex. And this, you can see it's going and then coming down with the visible light and going again with the UV light. Then I moved to Washington, D.C., and joined the Optical Sciences Division at the Naval Research Lab. I came initially to do an experiment using color-centered lasers that were developed at the Optical Science Division. I ended up spending, rather than 2 years as I planned, 21 years, and changing totally my career from really chemical research to material research, where I established this group of interdisciplinary group really of chemists, physicists, and material scientists, and established a section called the Organic Optoelectronic. This is a group picture here in front of the statue of Thomas Edison. This is, you see that when you enter the Naval Research Lab, the campus of the Naval Research Lab. And some of you may know that it was Thomas Edison's idea to establish a Naval Research Lab, a corporate Navy lab, to pursue fundamental research and applied research that is relevant to the Navy. So in order to develop this area of research, I had to really hire people that are not my mirror image in expertise, because I needed to have people that do synthetic work to develop photoelectroactive materials. Molecular surfaces and interfaces are important for the devices that I ended up pursuing, and then another group to make materials, to grow materials and fabricate devices and characterize them. So these are some of the facilities that we developed at NRL, a chemistry lab. This is another version of this is the connection with matrix isolation. So in a matrix, you disperse molecules in a rigid inert gas at very low temperature. Here we deposited materials at room temperature where we deposited a mixture of guest-host system, and I'll explain it a little bit later. And this machine here, we can do characterization in situ, or we can take whatever we deposit here, the substrate, they are movable, and do the characterization inside the dry box, which is filled with an inert gas. This is another chamber that we developed later, vacuum system that is directly connected to a dry box. So, since I was working in the Optical Sciences Division and not in the Chemistry Division, I chose to pursue areas of research that connects optics and chemistry. One area that intrigued me at the time was based on organic electroluminescence. I was encouraged to pursue this research area when I met Professor Tsutsui from Japan in a conference, who had been carrying this area of research for a while. And he encouraged me to do so because there were very few people in the States pursuing this area of research, maybe a handful or so. So I launched a research program on organic light emitting diodes. And these diodes are nothing but the basic element or the pixel of a flat panel display. So in order to generate full color display, you need to have red emitting, green emitting, and blue emitting OLEDs. And these primary colors are also important for white light emission or for solid state lighting. So why OLEDs? And I show you here the attribute and the advantage of why OLEDs. I'm not going to go through the details of that, but you can read them yourself. And just to show you some examples of products that were developed now in South Korea by Samsung and LG. Even though OLEDs were developed in Kodak by Shin Wang Tang in the 80s, unfortunately, Kodak did not have the vision to continue pursuing, supporting this research, and this area went first to Europe and Japan, and now the biggest producers of flat panel displays are Samsung and LG. And with this technology based on OLED, you can have transparent screens, you can have flexible screens, you can have, like your Apple Watch is in OLED and so on. It can also be used for lighting, all kinds of lighting. This ceiling can be just a long sheet of plastic emitting white light. So I'll just touch upon again some of the OLED research that I've done at the Naval Research Lab, and here I focus on a red emitting material where we synthesize some of these pentacene derivative, and again the link between this area of research and matrix isolation is in this emissive layer, where you have the guest molecules, which are pentacene derivative, are dispersed in a host. It can be a carrier transporter, electron transporter, like the aluminum hydroxyquinolate, and it's sandwiched between electron transporter and a hole transporter, and two electrodes. Just to show you, for those of you who are not familiar with the function of an organic light emitting diode, I simplified the picture here. So you can have a very thin layer of the organic emissive layer. It's much thinner than your hair, and it's sandwiched between two electrodes, a transparent electrode, which is typically indium tin oxide, and a low work function electrodes. So when this electrode, the cathode, when you apply a voltage, electrons or negative charge are injected, and holes or positive charge are injected, and when they recombine, you form an exciton. And you can form two types of exciton, singlet or triplet. I'm not going to go through the details of that, but the spin statistics dictates that the ratio would be you form 1 to every time you form 3 triplet exciton. And my area of research focuses on photon emission from the singlet excitons, which are called, which is fluorescence essentially. This is just show you the mechanism in more details about, you get electron hole injection, then recombination, exciton formation, and this is the path that we want to pursue, the emission from the guest molecule. So here I show you some fluorescence, steady state, and time-resolved fluorescence. This is the host emission, and this is the guest emission. And when we increase the concentration of the guest, you see the emission from the host being suppressed, and the emission from the guest is increased. And this signal that energy is transferred from the host molecule to the guest molecules. So using these compounds, I show you now the color gamut. And in order to get the pure red and pure green and pure blue, you want to be at the apex of these the triangles. So this is pure red, pure green, and pure blue. And we succeeded in getting very good red OLED based on this pentacene derivative. If you compare here the fluorescence, the PL spectrum, and the electroluminescence, this is, we see a difference in the host emission, which signals that there is another mechanism that we characterize, which the electron hole, rather than being recombined on the host and then transferred, energy transferred to the guest, they are directly recombined on the guest. We also, in collaboration with John Anthony, we developed other pentacene derivative with higher photoluminescence quantum yield. So the breakthrough really came when we started our collaboration with Chiso Company in Japan. They provided us these silicon organic compound called silols. And what's unique about these silols, they emit in the solid state. Usually when you have, usually the most highly efficient emitter is a molecule. When you form dimer and trimer and then grow the molecule, the emission goes down and down. But in this case, it's the opposite. These materials has fluorescence quantum yield that can reach up to unity in this case. We also found that they are very good carrier transporters. They transport electrons very efficiently. And here I show you a textbook example of an electron transporter, which is this silicon-based compound. And you show here the time of flight where you see the peak, and then either in nitrogen air, you get this plateau, and then it goes down. And this is really a textbook example of a non-dispersive carrier of charge. So its transport is non-dispersive and it's very fast. We were able to determine the mobility of it as in much, much higher mobility than at the time ALQ3, which was the reference that everybody has used. They are a good carrier transporter for two reasons. You have low-lying LUMO. This is the lowest unoccupied molecular orbital due to sigma star pi star conjugation. And they form very stable and aromatic dianion. So combining this compound for emitter, this emitter has a quantum yield of almost 100%. And with this electron transporter, we succeeded in reaching the theoretical limit for the external electroluminescence quantum efficiency for a fluorescent material. We also wanted to learn about the role that interfaces play in these materials, so we decided to do some ultraviolet photoemission spectroscopy. And we found that depositing a metal on an organic surface gives rise to an interface very different from depositing an organic on a metal surface. We show here the interface between magnesium, which is used, as I showed you, used as a cathode, where we are depositing it on the organic silol derivative. And what we found is that magnesium, which is a low work function material for injecting electron, we found that the electron injection in this case is mediated by a manifold of new magnesium induced states, and a charge transfer complex is formed, and this was confirmed by XPS and UPS between the magnesium and the organic, the silol derivative. So so there is this interface that mediates or facilitates electron injection and makes it more efficient. We also collaborated with a group of Jean-Louis Breda to do some calculation to understand why these materials, with very small change, I mean, these are very identical compound except for this element. We changed carbon for nitrogen here, essentially. And we wanted to understand why one is a very good electron transporter and the other one is not. Because both molecules have identical electron affinities and they have the same reorganization energies. And reorganization energy is a measure of the charge carrier mobilities. So we decided to grow crystals, single crystal, and it was a big challenge to grow single crystals because it's very difficult to grow organic single crystals, unlike inorganic materials, very simple to grow them. So we succeeded in growing one, but not the other. We were not able to grow the other one. What we found, there was no evidence of pi-pi stacking, which will encourage electron transport for this compound, which is the weaker of the two. So that's consistent with the picture of this compound not being as good as the other one. And we noticed that there is cooperative interaction between carbon-hydrogen and pi bond, which enhances the packing of the molecules. So it's fairly tight packing. So we see that there are several CH groups that act as donor for this CH-pi interaction with nearly this phenyl group in an edge-to-face position. We found that the LUMO wave function, this is from the calculation of both molecules, are mainly localized over the silyl ring and the phenyl rings in the position 2 to 5. And the LUMO transfer integral for the dimer is calculated to be about 5 MeV. And we compared that to one of the good electron transporters, which has, this is called the bethylphenanthrolene, which has a transfer integral of about minus 35 MeV. And from there, we were able to determine the electron mobility of this compound. One problem with these compounds were that they were not very stable, and they tended to easily crystallize. So after studying these compounds that we got from Tissot company, we decided to make our own compounds, hopefully that are going to be amorphous and more stable. So we launched on preparing these spirosilyfluorines, which are excellent emitter in the ultraviolet and have fairly good glass transition temperature. Then we got more ambitious. Well, we did some characterization of the crystal structure as well. We grew a single crystal of these molecules, and this is interesting because the crystal displays a remarkable packing scheme, and you have 6 different kind of conformers that are arranged in a very efficient way. This is a more a closer look at the packing, which shows a very tight scheme, and you get very close form very close hydrogen bonded to carbon. You know, this is very small numbers for this type of interaction. But we got more ambitious, and we decided to develop another class of spirosilyfluorine, in this case the asymmetric one. And these turned out to be very challenging synthesis, and it took Sang-Ho Lee about a year to develop this very complicated and tedious synthetic scheme. I'm not going to go over that, but I'll give you the end product of the result, which is that we succeeded in making, rather than crystalline materials, amorphous material, which are much better forming films when you deposit them or you spin coat them. And their glass transition temperature are much higher than any of the silos. So going from the one that we got from Tissot, 77 degrees centigrade, we were able to triple the glass transition temperature. And with that, I am going to wrap up and just, more information at the time. If you want interested in more information, we published this book in 2005 that has a lot of information about the research that have taken place at the time. And just want to mention something. About 14 years ago, we celebrated the 125th anniversary of the light bulb, of Thomas Edison light bulb. The same year, GE developed a 24-inch by 24-inch panel based on a white OLED, producing 1,200 lumens of light and luminous power efficiency of 15 lumen per watt. This is on par with, at the time, the 60-watt incandescent bulb. Now, this has been surpassed by an order of magnitude. So now you can go to Best Buy and buy a 77-inch LG OLED TV, and you can enjoy this very beautiful OLED TV just by going to Walmart or Best Buy. And it took about 30 years of the discovery of, or the development of OLED by Xinhuan Tang to be now benefiting from this technology. And this is, by the way, the best technology for any flat panel displays. You know, you have liquid crystals, you have plasma TVs. This is by far the best. And again, I would like to thank the committee and my nominator for awarding me the Hillebrand Prize. Thank you.
What were the OLEDs for? Why were you studying them at the Naval Research Lab? What did they do with them first?
Well, I mean, the Navy was interested in developing these flat panel displays for computers and things, you know, for the soldiers, you know, to have access to, direct access to information and data.
So for the Navy work, does that mean that what you did, you could see a display and easier in sunlight, things like that?
So one of the attributes of this, an advantage of these devices based on OLEDs is these are self-emissive materials. Typically, if you look at your TVs, most of the TVs are based on liquid crystals. So you need to have an external light source for, you know, for the polarization of the liquid crystals, so you can get, you know, your color scheme this way and the TV. And here you don't need that. They are self-emissive, so you can see them in sunlight. And that's very important. Thank you, Pat, for this point. That's important for the Navy because you have the Marines or walking in sunlight and they want to get information. They would, I don't know if you remember the old, at least the old phones, you could not read them in sunlight. Right now, you can't read them in sunlight because of this attribute, the self-emissive nature of this material. And they are very bright OLEDs. I mean, the OLEDs are very bright. There is another technology based on not organic but inorganic LEDs. And these are the LEDs used in traffic light. Like when you see a blue traffic light, it's based on an inorganic LEDs. The advantage of those are they are high temperature material. They can survive very high temperature. The organic, you have to be careful how high a temperature you can go. The other thing also, not only for OLED, that's very interesting, like, you know, liquid crystals. If you have a liquid crystal displaced in your car and it's very cold outside, the screen will freeze and you will not see anything, you know. But with these, you know, these are actually better emitter as you go lower in temperature. I'll tell you, I mean, it was technical and non-technical. The first time, I was a kind of a fish out of water in the optical sciences division because I was a chemist. And I was surrounded by physicists and electrical engineers. So when I first proposed the idea of developing organic light emitting materials and devices, my audience or the people who were evaluating my talk, they were laughing at me and said, "Oh, these will burn. These, you know, this organic means carbon-based essentially. They will burn, and they are not stable." And I responded, "Well, you can develop material that are stable and can withstand high temperature. It depends on the functionalization of the material." So my first challenge was to convince the chemists, the physicists and the engineers in my division that this technology is feasible. The next challenge is to develop a team. As I mentioned, I had to hire surface scientists. I had to hire organic chemists. I'm a physical inorganic chemist. Organic chemists to synthesize the compounds. So I had to form a team of interdisciplinary research that are, you know, so most of the people that work in my group did not have the same areas of expertise as mine. And that was a challenge, but it was also very enriching for me. I learned a lot from all members of my team, and I thank them all for their contribution, you know, because I couldn't do it on my own. And this is really the nature of science these days. Most of the work these days requires expertise from different areas, cross-disciplinary and interdisciplinary in nature. The challenge from a scientific point of view for me as a person, as I showed you, I was trained as a chemist, growing materials and characterizing them essentially on the surface or a film or so forth. The biggest challenge for me initially is to make devices. I did not know that if you make a device today and under and use the same condition, 2 weeks later, you're going to get a totally different device. When you grow a film today and use the same condition and grow it next week, I'm sure I'll get the same properties. This is not true. So making a device was a big challenge for me, coming from my background and training. So this is kind of the challenges in the lab. And but after that, I learned. I mean, the biggest thing I learned is a PhD teaches you how to solve a problem. It doesn't teach you, very few people continue all their career to pursue the same type of research. Many of us go on to different areas of research, and in fact, my career and my journey has been totally nonlinear, and it's ironic because when I went to the Naval Research Lab, I did nonlinear optics for a while, and it was ironic because the last time I learned about optics was in physics course in high school. So anyway, you live and learn, and it's important to be open-minded and I think I learned a lot about myself too. That I can launch in a new area I know very little about, and study it, read the literature, talk to colleagues of mine, and go to conferences and listen to what people have done, and then develop it this way. Did I answer your question?
Yes.
Okay, thank you.
Hi.
Hi.
So, kind of a two-part question.
Sure.
So, it's just curiosity. You mentioned applications to business. Did you ever receive offers from like IBM or places like that, or Samsung? And if so, why did you choose to work for the government and choose not big money? Just kind of a personal question.
Well, I personally, originally I was interested in pursuing a career in academia. I never thought about corporate America as a place for me as a person. I wanted to do research. Research was my passion really more than even teaching. And so that's why I pursued research. But in my team, I had, I don't know if I had a picture of him, but one of the people in my team was from Samsung. He was actually working for Samsung in South Korea, but his family, especially his kids, did not like the way they had to study until midnight every day. So his family moved before him back to the States. He did his PhD in the States, and he came back to the States without even having a job. He left Samsung. And then I met him in a conference, and he approached me, and I hired him. And he's now a section head, actually, in the Optical Sciences Division at NRL. So, money is not everything. You have to have satisfaction, and so this was my interest, is to pursue research. Thank
We're
you.
very, very proud of you. My question to you is, have you faced any challenges being a scientific chemist, optics, physics, math, etc., in the United States versus in Egypt or anywhere? Have you faced any challenges being a minority, a woman?
Challenge I faced actually late in my career, ironically. When I joined the group of Jean Margrave at Rice University, I was the only woman in his group. He had, I think, 20 or 25 people, male, working for him. And they were all very nice to me. Actually, I felt like a princess working there. And he was a father. I call him my father in chemistry. He was a friend. He was a good colleague. So as a graduate student, I had no problem. unlike many other female scientists I know that have had faced many challenges. The first challenge I faced was actually when I joined the Naval Research Lab. Discovered when I was at NRL that there were 6% women scientists there and engineers, and yet when you look at the leadership positions, there were none. Nobody. And what we decided to do at the time, we started developing what we called a WISE network, Women in Science and Engineering Network. And they had this science lounge at NRL, so we used to meet once a month, all the women that were interested to participate, and have lunch, a pizza or something, and discuss and interact with each other. These are women from many different divisions. And we formed what we called the analog of the old boy network. And it was very empowering, to learn about, we got information and things because we did not get it from our male colleagues. Then we developed, Kay Howell and I developed a mentor program. Actually, when we went to Dr. Kafafi, at the time the director of the Naval Research Lab, we went to tell him we would like to develop a mentor program. He said, why? Your bosses should be a good mentor. I said, if this is the case, we would not be here. So we launched a pilot project and developed a mentor program for all scientists and engineers, men and women. And we did this pilot project for a whole year, and it was a great success. And then it was established as part of NRL. I'm not sure how well they are doing now, but NRL now has an acting associate director, one, under the director of research. It has a woman division director at least on campus in Washington. And it has a head of a center for biomolecular science and engineering that is a woman. So things are improving a little bit, but definitely. And I was actually, there was a woman section head before me that left the optical science division, and I was for a while the only woman section head in optical science division. But it was an uphill journey with a very high activation energy for the chemists in the crowd.
Any more questions? Thank you.
Thank you.